Bismillahirrahmanirrahim. In this video, we are going to discuss that how we can calculate the phase margin, gain crossover, and the phase crossover frequencies. In the previous videos, we have discussed about the stable and the unstable system, and we have discussed their body plot, polar plots in detail. I am going to briefly revise the body plot and the polar plot for the stable and unstable system. So if you look at this one, in the first diagram here over here, this is the body plot of our system, and the frequency at which the gain of your system is 0 dB, right? That is said to be the gain crossover frequency. So I'm going to mark it omega GC, and the frequency at which the phase of your system becomes minus 180 degree, this is said to be the phase crossover frequency. So at gain crossover frequency that you can observe over here, if your phase is above minus 180 degree line, then this is said to be the positive phase margin. Because how you determine the phase margin? Phase margin is determined like that it is equal to phase of your system plus 180 degree at the gain crossover frequency. So at gain crossover frequency, that is when the gain of your system becomes 0 dB. So at this point, this is the phase, right? And if we add 180 degree in that one, you will get the positive angle because this is above the minus 180 degree line. So this difference, this one, that is how much your phase is above this minus 180 degree line, is basically the phase margin, and this is considered positive if your phase is above this minus 180 degree line. Means your phase is greater than minus 180 degree, that is minus 120 or minus 110 or anything above that one. Okay, so this is the positive phase margin. Now if we look at the phase crossover frequency, that is when the phase of your system is minus 180 degree, at that point the phase the gain of your system is less than 0 dB. So that is considered as the positive gain margin. What is the gain margin? Gain margin is basically this difference, that how much gain variation is available such that your this point is going to cross this axis over here. So we have this as the gain margin, and if it is less than the 0 dB line at this point, if the gain of your system, it is considered as the positive gain margin. We are going to increase the gain, right, to lift this body plot up so that it passes through the 0 dB point at that frequency. So this is the positive phase margin. And if your phase margin and the gain margin is positive, this is the gain margin, it is positive, and the phase margin, this is positive, then your system is said to be the stable system. Now for the unstable system, this is the body plot. Here you can see that at the phase crossover frequency, the gain of your system is in the positive dBs range, right? So this is considered as negative because we will have to decrease the gain to bring this graph to pass through this 0 dB point at that particular frequency. So this is the negative gain margin because your gain is above 0 dB, right? So this difference is basically the gain margin. And similarly, if we look at the gain crossover frequency, that is this one, at this the phase of your system is lesser than minus 180 degree, that is, let's suppose minus 210. So this phase is also considered as negative. The phase, as I told you, the phase that is below minus 180 degree, and if it is, let's suppose, minus 210 degree, and if you add 180 degree with this one, so you are going to get minus 30 degrees. So this is the negative phase margin, negative phase of this system. And if the gain margin and the phase margin, if they are negative, then your system is unstable. So you can look at the stability of the system looking at the body plot of that one, that how much margin you have, how much variation in the gain is possible. Because if you are changing the frequency and if you have the gain of the system in such a way that this is going to cross somewhat like that, if this phase plot is same, so at that point your phase margin will be negative. If phase margin is negative, and then your system is unstable, and your phase margin should be positive for the stable system. So we have seen this body plot and this one for the stable and the unstable system. Now let's discuss about the polar plot. The polar plot is basically the plot of your transfer function, real and the imaginary part, when we are going to replace s with the j omega, and we are going to vary the frequency from minus infinity to positive infinity. So from in this graph, basically we consider from infinity to 0. If we have the variation from 0 to infinity in the frequency, and then we plot the real and the imaginary part. We have discussed in the previous videos. Okay, so now let's suppose that for a particular transfer function, this is the polar plot, and this is the circle of unit radius. This is the unit circle. So when the polar plot is going to intersect with this unit circle point, so this frequency is basically the gain crossover frequency. Why gain crossover frequency? Because at this point the magnitude of the system is going to become 1 and the log of 1 is 0. And so if at this point the dB gain is going to become 0, that's why this is the gain crossover frequency, right? This is corresponding to that one. This was the gain crossover frequency, and this is represented over here whenever your polar plot is going to intersect the unit circle um, in the polar coordinates, in the polar plane. Okay, so this is the gain crossover frequency, and the phase crossover frequency is this one, omega pc, right? Because at this point your system is going to have only the negative real part, and if you calculate the phase of that one, that will be minus 180 degree. So this is basically the line of minus 180 degree. So when the phase of your system becomes minus 180 degree, the corresponding frequency is said to be the phase crossover frequency. So that is this one, if we correlate these two. So if your phase crossover frequency, that is this one, when your polar plot is going to intersect this negative real axis line, and if it is if this intersection is within the unit circle, then it means your gain margin is positive. How you define the gain, how you calculate the gain margin from the polar plot? The magnitude of your transfer function at this frequency is this one. So 1 by that magnitude is basically the gain margin, right? And it gives you the information that how much variation you can have in your gain, such that your system is stable, and its magnitude is within this range minus 1. If this magnitude is like this, that it is crossing, it is outside the unit circle, that is this one, then your system will be unstable. We have discussed in the previous video. So this intersection, this point of the phase crossover should be within the unit circle for the unstable system. For unstable system, it is outside this circle, that you can observe over here. This is representing the stable system, and this one is representing the unstable system. So this is the um, phase crossover frequency, and at this point the magnitude of your system is above 1, so it means you will have to decrease the magnitude to bring it stable. So that's why it is the negative gain margin, right? So gain margin is calculated as 1 by kg. What is kg? Kg is basically the magnitude of your system when your frequency is equal to the phase crossover. Okay, so this is the polar plot for the stable system. Here you can see, and the phase angle is also the phase margin is positive. What is the phase margin? This is the gain crossover frequency. So at the gain crossover frequency, what is the angle? If I correlate it with this graph, here you can say gain crossover frequency, the angle, the phase of your system is this one. So let's suppose that this is this one, this is the phase of your system, right? So how much difference is available from the minus 180 degree line? That is basically the phase margin. And how you get that one? As I have written over here, phase margin is equal to phase plus minus plus 180 degree. So this is the phase, and if you if this is the negative one, and if you are going to add 180 degree in that one, you are going to basically get this angle gamma, right? So this is considered as positive. It is in this half of the plane. Okay, so this is the positive phase margin. right? And if this angle is somewhat like that, if it is crossing over here, then if you add if you calculate this angle and then you add 180 in that one, you will be getting the negative one that is shown over here. And if this is the phase of your system, and from that if you add 180 degree in that one, so you are again going to get the negative one. So this is considered as the negative phase margin, right? Let's suppose this angle is minus 210 degree and going to add 180 degree to that one, so you are going to get minus 30 degree, that is minus 30 degree over here. So angle in this direction will be considered as the negative one. So this is the negative phase margin. And similarly, this one is the magnitude. So 1 by kg of that one, as it is greater than the magnitude is greater than 1, so 1 by kg will be smaller than 1, and the dB gain of that one will be negative. So you have the negative gain margin of the system. So if your gain margin is negative and phase margin is negative, your system is unstable. This diagram is going to show you the graph between the magnitude in dBs and with respect to the angle, the phase in degrees, right? So for a stable system, this plot will be somewhat like that, right? So your intersection with the um, minus 180 degree line will be at the phase less than the 0 dB, that you can see the negative dBs are over here. So at minus 180 degree point you have this intersection, that is the that is going to represent the stable system. If you look at from here at minus 180 degree point, your gain is this one. So your gain is less than 0, right? And it is the point of minus 180 degree phase. And similarly, if you look at the phase margin, so phase margin when you have the 0 dB point, that is this one, so that is corresponding to this line over here. So 0 dB line, so at 0 dB line your phase is for a stable system phase margin is positive. So this is positive phase margin if it is in this direction of this line towards the higher angle with respect to that one, minus 180. In this direction there is the positive phase margin, and in this direction there is the negative phase, there will be the negative phase margin. So for a stable system, you can have this graph between the dB gain and the phase angle of your system. And for unstable system, the same graph will look like this. So at this is the line of minus 180 degrees, so your phase of your system is below that one, because this angle is negative, so that's why I'm going to consider, let's suppose minus 210 degree, right? So it will be over here. So you have the negative phase margin, and similarly you have the negative gain margin because your gain is positive at the angle of minus 180 degree, positive dB gain. So this is representing the unstable system. You can have the polar plot in which you are going to cross the negative real axis a number of times. So these are the different phase crossover frequencies, omega 1, omega 2, omega 3. All of these are the phase crossover frequency. If your polar plot is somewhat like that, when you have the frequency, let's suppose, equal to 0, and when you are increasing the frequency going towards the infinity, so you will be having the multiple crossovers. So there may be the multiple crossovers over the negative real axis, and it means you have the multiple phase crossover frequencies. Similarly, your polar plot may be like this, crossing your unit circle number of times, so you will be having number of gain crossover frequencies, omega 1, omega 2, omega 3. So there are 3 gain crossover frequencies in this particular case. Okay, now let's look at the example. This is taken from your textbook. So this is a closed loop system shown in front of you, that is k over s into s plus 1 into s plus 5. So here you can see the sketch of the body plot for this closed loop system for the different values of the gain. First of all, we are going to consider this gain is equal to 10. So if the gain is equal to 10, your body plot is like this. So over here, if I observe this one. This is the 0 dB line, right? And this is the frequency at one particular frequency, and when your gain is going to become 0, so this is the gain crossover frequency, right? And if I take this line in the phase plot, minus 180 degree line, your phase of the system is going to become minus 180 degree over here. So this is the phase crossover frequency. So at the phase crossover frequency, if you observe this one, your gain is about 8 minus 8 dB. So you have the gain margin of plus 8 dB, means you can increase the gain by 8 dBs such that it will cross the 0 dB line at this frequency. So you have the margin of 8 dB, right? And if I look at this point over here, so your phase is 20 degree above this line, minus 180 degree line, and 21 degree above. So it means your phase margin is positive. So phase margin is positive and the gain margin is positive, so your system is stable for the gain k equal to 10 in this case. Now if we increase the gain, and let's suppose it becomes 100 over here. Now let's look at the body plot. The body plot is obtained from the MATLAB. I'm going to sketch the 0 dB line over here. This is the 0 dB line. So this is the gain crossover frequency omega gc, and over here I'm going to sketch the line of minus 180 degree. So this is the frequency omega pc, phase crossover frequency. So now let's look at it at gain crossover frequency. The phase of your system is this one. It is minus 30 degree below this minus 180 degree line. That is minus 210 degree at this point. So your phase margin is negative. And if I look at this phase crossover frequency point, so at this point your gain is 12 dB above this 0 dB line. So you have the minus 12 dB gain margin. You will have to reduce the gain by 12 dB so that it crosses the 0 dB line. So this system is an unstable system because your gain margin is negative, your phase margin is negative, and if for the lower gain, when the k was equal to 10, your system was stable. If you are increasing the gain, your system is going to become unstable. So with the variation of the gain k, your system can become stable and unstable. For one particular value of the k, when your gain margin and phase margin will be 0, it means at that point your system is right at the boundary of stability. Right after that is going to become unstable. So your closed loop poles will be at the j omega axis, because after that the poles will be entering into the right half plane if your gain is further increased, and your system will become unstable. And below that value of the k, your system, your closed loop poles will be in the left half plane and your system will be stable. Okay. So now let's look at an example in which we are going to calculate all of these things. So we are going to calculate the gain margin, phase margin, gain crossover, and the phase crossover frequency for this particular transfer function. So what are the steps? First of all, you will have to replace s with j omega to get the sinusoidal transfer function. So if you replace s with the j omega, you are going to get this transfer function, right? S with j omega over here, j omega over here, and j omega over here. So now let's find out the magnitude of that one. So magnitude of 1 and the magnitude of j omega is simply omega. The magnitude of this part 1 plus 2 j omega is 1 plus 4 omega square, and the magnitude of this part is 1 plus omega square. So this is the magnitude equation for your transfer function. And what is the phase equation? The phase of this constant part is 0, and the phase of this part will be subtracted from the numerator. So it all of these, the phase of this and this will be subtracted from 0. So it is minus, it will be considered as negative. So minus tangent inverse of infinity. Why infinity? Because its real part is 0 and the phase is imaginary part over real part. So omega over 0 is the infinity. So tangent inverse of infinity is the phase of this one, then minus the phase of this part, its imaginary part is 2 omega and the real part is 1. So you can see the 2 omega over here, similarly omega over here. So this is the phase equation. And we know that at the phase crossover frequency, this the phase margin of the system should be equal to minus 180 degree. So we are going to put this phase equal to minus 180 degree, and at that point this omega will be equal to omega phase crossover. So that is this one. For omega is equal to omega pc, that is the phase crossover frequency, the phase of your system is minus 180 degree. So we are going to take it equal to minus 180 degree, and we are going to put this equal to like this. Now if we do simple mathematics, we rearrange this equation. So we tangent inverse of infinity is first of all minus 90. Taking this minus 90 on this side, this is going to become minus 90, and then changing the sign, so we are going to get this equation. Now if we take the tangent on both sides, we are going to get this equation, tangent 90 and tangent of this one, and then using this trigonometric identity, that is tangent a plus b is equal to tangent a plus tangent b divided by 1 minus tangent a tangent b. So applying this one over here, because we have taken the tangent, so this is the term a and this is the term b. So applying this trigonometric identity, you are going to get this one, tangent of tangent inverse of 2 omega bc and tangent of tangent inverse of omega bc divided by 1 minus this term. So these will be cancelled out, you will be left with 2 omega pc, and similarly this will be cancelled out, omega pc, and this will be giving you this term, and this will be cancelled out, and you will be left with omega pc. Okay, so this can be written like this, and tangent 90 I can write it like that, because this is equal to infinite, so I can write it like that, 1 by 0. So 1 by 0 equal to this term, and by cross multiplication I am going to get this one. So omega pc square is equal to 1 by 2, and the omega pc is equal to 1 by under root 2, that is 0.707 radian per second. So the phase crossover frequency for your system is 0.707 for this transfer function. Now let's calculate the gain margin. So how we calculate the gain margin? Gain margin is 1 by the magnitude of your transfer function at the phase crossover frequency, right? So this is the gain margin, right? So gain margin is 1 by magnitude of your transfer function at phase crossover frequency. So phase crossover frequency is 0.707, right? So we will be calculating the magnitude at this point at the phase crossover frequency. And how to find out the gain margin in dBs? You will be taking 20 log of that gain margin, so you will get this expression, right, like this. So taking kg equal to that one, because kg is equal to 1 by magnitude of your transfer function at the phase crossover. Okay, now let's calculate this gain margin. At omega is equal to omega pc, the phase is minus 180 degree. So if you express your sinusoidal transfer function in the real and the imaginary part, as the phase is minus 180 degrees, so your real part will be negative and the imaginary part will be 0. Because if this is the condition, then you can have the phase of minus 180 degree. So we have this transfer function, sinusoidal transfer function. We are just going to simplify it. Here you can see some mathematical steps, and if you simplify and you represent in the real and the imaginary part, it will be like this, right? And the imaginary part will be 0 for the phase crossover frequency, right? So this only real part will be there. So in this you can take out the omega square as the common out. Omega square, if you consider common out, so this will become omega square and this will be cancelled out. So now considering this real part, minus 3 by 9 omega square plus 1 minus 2 omega square whole square, right? So we know that the omega phase crossover is 0.707 radian per second. So now let's calculate the magnitude of the transfer function at this phase crossover. So that is this one, and after placing the value of the omega phase crossover, we are going to get this one, and the magnitude comes out to be 0.667. So now 1 by the magnitude at the phase crossover is the gain margin. So gain margin is this one, 1 by this, so that is 1.5. And in terms of dB gain, so you will have to take this kg in the dB, that will be equal to 20 log of 1.5, so that is 3.52, that is the positive gain margin, right? So this is the positive gain margin. And now let's calculate the gain crossover frequency. the frequency at which the magnitude of your system is going to become equal to 1. So at gain crossover frequency at omega is equal to omega gc, your magnitude is equal to 1. So it means 20 log of g of j omega will be equal to 0, right? And let's set up the magnitude equal to 1, and it means 1 by omega under root 1 plus 4 omega square and under root 1 plus omega square, that should be equal to 1. Okay, now we want to find out the frequency at which this equality will be established, that this side should be equal to this one. So first of all, let's consider that omega is equal to 1. At omega is equal to 1, if we calculate this g of j omega, that is going to be 0.3, and this is not equal to 1. It means omega is not equal to 1. I am going to use error and trial method for the trial and error method for the evaluation of this gain crossover frequency. So now let's take omega is equal to 0.5. So if we evaluate the magnitude of the transfer function at 0.5, so this comes out to be 1.26, and it is greater than 1. For omega is equal to 1, it was 0.3, lesser than 1. So it means our actual frequency is somewhere in between 1 and 0.5, because we are looking for that frequency at which this magnitude is going to become equal to 1. So if you play with that, and if you calculate and you make the segments, I have just shown you the final value. If you take omega is equal to 0.57, so magnitude is equal to 1.0037, that is nearly equal to 1. So the gain crossover frequency is nearly equal to 0.57 radian per second, right? So we are taking the magnitude equal to 1, and the dB gain will be equal to 0, because 20 log of 1 will be equal to 0. So 0 dB gain or the magnitude equal to 1, the frequency at which this condition will be established, that is called the gain crossover frequency, and that is 0.57 radian per second. Okay, now after calculating the gain crossover frequency, we can now calculate the phase margin. So phase margin, the phase equation for this transfer function can be written like this, that is minus 90, because this is j omega, the phase of this one, the phase of this part, and the phase of this part, right? So minus 90, and this will be tangent inverse of 2 omega gain crossover, and minus tangent inverse of gain crossover. So gain crossover frequency is known, just place the values, simplify that one. So gain crossover phase is minus 168 degree. So how to find out the phase margin? Phase margin is equal to 180 degree plus the phase at the gain crossover frequency. So this is going to give you 12 degrees. So you have the phase margin of 12 degree for this transfer function. So phase margin is positive, and your gain margin, if you look at that one, this is 3.52 dB, this is positive. So it means your system is stable. So this particular system that is being represented by this transfer function is the stable system. So if I conclude the video, we have seen what do you mean by the stable system in terms of the body plot, in terms of the polar plots, and the magnitude and the phase plot. And then we have seen an example at how we can calculate the gain margin, phase margin, gain crossover, and the phase crossover frequency. That's all from this video. Thank you very much.